And I thought the two of them together were very interesting. So here's the email. Okay, so I know it's small and kind of long, so we'll kind of read it out loud together. Why isn't that on back there? Projector. Okay, so I have a few concerns with how well I will do in your course just because of your teaching style. Isn't compatible with my learning style. Back in high school, math was my strong subject. It was my favorite subject because I was always a student who called out the teacher's mistakes and who the teacher would ask if a problem was done correctly. I'm very good with numbers, but so far your class, Calculus 1, has not dealt with numbers at all. I'm having such a hard time trying to understand your way of teaching, and I feel like a different professor who uses numbers and equations rather than words and explanations of why we do things would suit me better. So my question is this: will we be getting into numbers soon so I can exercise my ability, or is this class going to continue like this? I admire the fact that you really want the students to learn why we do things, but the learning technique isn't for me. Please let me know if the class will begin to deal with mathematical equations before I switch professors.
My big question is, are they a math major or engineering major? Because I haven't taken a single computational class in the math field here at ASU.
I'm not sure what her major is. Not sure what her major is. So reactions to this. What do you think? Ashley?
Well, I mean, I will say, I think I took either Calc 2 or Calc 3 with you a few years ago, and I really felt like the same way when I first started, like that the student did, of like, what is going on? Like, I used to be good at math, and this is really difficult. But I obviously stuck with it and got through it. But and then I started taking all the methods courses with you, and then I, started to understand it more. But I definitely understand like a student like this, because I was like that too, of being taught one way your entire life, and then the one person who shows you a better way to do it, you fight it a little bit because it's different from what you're used to.
Yeah. Other reactions? How about?
I was the same way, kind of, when I first took my Calc 1 class. And I remember it being really challenging to get over the, not having equations and not being shown, step by step how to do the problems. But once you adjust to it and just kind of, go with it, and I feel like you have to adjust your learning style to work with the teaching style sometimes, too, because, you're always going to have teachers that'll teach differently than the way you learn, because teachers can't teach it every single teaching style all the time. I feel like that makes it really challenging.
If I can kind of direct our discussion, my reaction to this, my thoughts were about her high school teachers. My thoughts were her high school teachers and how she got to this point. And so maybe any comments on that? Brianna?
I almost think it's kind of sad that if she or he can't understand things because their high school teacher taught them to only understand the process and give them every example for every situation, then they don't actually understand the problem. They only understand the patterns of how to do things.
Mm-hmm. The rules.
Yeah.
Chrissy, were you going to say something?
They don't know where to use it.
Okay.
They know the processes, but they don't know where to use it. So, in their mind, it's just numbers. It doesn't have to do with science.
Okay. Jason?
I mean, to be honest, I can kind of connect with her. I was the same way in high school. Math has been my strong subject, and since I've been here through the Calc series and everything, I've struggled. I've had different types of teachers. I failed Calc 3 the first time because it was just computational. It was just formulas, everything like that, and I thought that was my learning style, but it wasn't. And then I was able to take it with you with a different learner teaching style, and it helped. I still struggled for sure, but it helped. And I don't know. I think it's just one of those things where it is sad that she wasn't able to myself learn why things happen as she went through the math process through high school, because when you get into the higher learning and the college level math, they don't they don't ask you strictly what the answer is. I mean, professors want to know why it works. So it's like not being able to explain that. I mean, you're kind of setting yourself up for failure.
Okay, just do one or two more.
I was just going to say it concerns me as a future high school teacher that I'm going to have 150 of these types of students sitting in front of me, and my fellow colleagues in the classrooms around me will be teaching this way. And if I want to teach more to understanding, I'm going to face a lot of resistance on both sides of that.
For sure.
Just to go along with that, at my internship, there was like 3 teachers that all got together, and this is exactly what they were discussing. Because there is a teacher who taught them how to calculate a more exact imperfect square root, where it's not a whole number, where it's just this like procedure that they go through that makes absolutely no sense, but if they go through it, they get the right answer, versus the way that they'd been teaching, which involved more understanding, and then they didn't know, well, do I teach it the way that I've been teaching it, or should I teach it for the right answer? And they have their students mix up a lot. Do we need to teach both? Because we're going to get 2 different kinds of classes. And I don't know. It's kind of hard when you've got one teacher teaching one way and another teacher teaching a different way, and all the students mix.
Yeah, so many of you have been through 42, and you read the teaching gap. I just want to show a few things relative to that in terms of so here's some stats, and this is 1975. This is natural science and engineering degrees for 24-year-olds. So how many basically a percentage of natural science and engineering degrees. Back in 75, we were among the leaders. Only China, and maybe Finland was tied with us, but Japan. Only Japan exceeded us. And so now we fast forward to 2000. Where do we stand internationally? Okay, so we're way at the bottom here. So what's going on? Why is it that students are choosing against science and engineering? Okay, or they're trying and maybe they're not succeeding. So why is this? And then another nice so this was directly from that study that was in the teaching gap, where they compared Germany, Japan, and the U.S. The transcripts were analyzed, and the transcripts they were stripped of any nationality from them. So the people that analyzed the transcripts had no idea which classroom the countries came, which classroom from which country it came, and then they coded them based on quality of instruction, and they had a way of saying high quality instruction, medium, and low. Okay, so Germany was about 1/3 of each. Japan was higher in high and medium, and eliminated the low. And so, what percent from this study would you think that U.S. had high, what they're calling high quality instruction? What percent of the lessons or time? He said it was really low. Yeah, it's really low. Okay, so, and low was 89%. So 89% was what they deemed as low quality. And so what kinds of things would that equivocate to? Like what is this low quality instruction? What would you guess that is?
That teaching to the test isn't working.
Okay, but so specifically what kinds of things? What does the American classroom look like that 90% of the time is deemed as low quality instruction?
This was 13 years ago.
So I would say like teachers standing in front of the classroom, telling something, giving kids worksheets, them doing it, turning it in.
Okay, so replicating problems. Okay, so has it improved in 13 years?
I don't
Yeah.
know what it was 13 years
Yeah,
ago, but
so-
I'm figuring it hasn't probably changed too much.
I'm doing my own research here, so I'm looking for more recent things in terms of international comparisons. But I don't think it's changed
Yeah,
or
I
improved
don't think
much.
it's changed much.
Yeah.
In high school or college as well, or just high school?
These were middle school math
Oh,
classes.
middle school, okay. Oh, okay, sorry.
So I guess my encouragement to you is like, so you are the next generation of high school. You're going to be teaching the middle school and high school kids. And so, do you want your students sending their calculus teacher an email saying, I was the best in my math class, but I have no idea what you're doing? When you're trying to teach me the rich ideas of calculus. Okay? So to take calculus and to make it into learn how to do section 1 problems and learn how to do section 2 problems and learn how to do section 3 problems is, to me, is a very sad thing, because calculus is such a beautiful subject. So much going on in terms of relationships and ideas. And so in high school, to get them ready for calculus with just a calculational orientation is going to be, it's really tough.
I think it might be a good idea to look at their elementary experience with math.
Yeah, true.
Because a lot of times those teachers have taken 1, maybe 2 courses of elementary ed math. And I've heard from numerous teachers that, numerous middle school and high school teachers say that they don't focus on it in elementary because that teacher does not like math.
Yeah, it starts at the beginning. It starts at the beginning, and then in 12 years, it just becomes reinforced.
Well, that's kind of the reason why I'm actually thinking about going 7th, 8th grade, and then actually going back and getting a middle school one where you can actually teach 5th and 6th grade, and then be able to help the students get up to that level of thinking a little bit earlier.
So I'm going to, like I said, I'm still doing some more research on more recent studies that have been done with international comparisons, and we'll see how the U.S. is doing a little more currently. But yeah, so I hope I can influence you to really, even if students aren't going into calculus, in terms of, like you talked about, just facing life and being a problem solver in real life. Teaching them all these methods and arithmetic for 12 years of their life isn't going to help them with that.
Well, I don't know if anybody else was like this, but I actually got the calculus done with all computation. Or, sorry.
Yeah, it's
all computational, and I didn't understand it one bit.
it's possible to teach a calculus course that way. It is possible to do it.
I literally got the teacher fired because nobody understood anything else on that class.
Yeah. So it is possible to do it, but it's a very sad thing to me when calculus is such a powerful, rich, idea-loaded subject. Okay, so I want to talk about. I started to grade your. I've got all but one of the graphing calculator projects done, and so I wanted just to talk a little bit about good mathematical solutions on these and versus shape thinking. I kind of mentioned shape thinking. So here's just a little kind of one versus the other. So a good mathematical solution, I wrote, is developed based on understanding and problem solving. So not looks right. That goes over on the other side.
You have this up on,
What's that?
you have this on Blackboard at all, or?
I don't. Okay, so let me that. Okay, so good mathematical solution developed based on understanding and problem solving. Okay, so it's really, understand, and you've really thought hard about it to come up with a solution. Shape thinking, on the other hand, would be just your trial and error until the image comes out right. Okay, so you keep trying different things, and you're not really engaged in critical thinking, and you just, maybe if I put a 2 here, or maybe if I switch them, then it'll come out right. And then when it comes out right, you're satisfied. Okay, so that's shape thinking. Okay. Another aspect to a good mathematical solution is it's clear when you see the solution, when you see maybe it's in graphing calculator, you see the command line, someone else could look at it, and it's clear how it relates to the original question and whatever givens there were. Okay, but then shape thinking, the solution might turn out after this trial and error process with no seeming connection unless someone was there to explain it. Okay, another aspect of a good mathematical solution is it could be generalized to solve many similar problems easily. So you could just kind of tweak it to make it more general, and and then it could be very powerful in solving any type of similar problem. But with a shape thinking solution, every time you had a new maybe set of inputs, you'd have to recreate what you came up with, okay? So what we're really going after is to avoid this, to recognize when you start to do this, and step back and say, hey, I need to start thinking about this, and being a little more, using a little more forethought and know what's going to happen when I type something in, rather than I just got to get this assignment done, right? I just got to get an answer and so I can turn this in, right? So that's the student in you, right? Okay, so what we want is to try to move towards this. And so, but this is hard work, right? So if you come to a problem and it just seems like I can't get it, right? I can't get it, and you're really tempted to just go for the trial and error. So this takes hard work, and maybe you sit there and you think about it, and you ask a question, and then maybe you have to come back to it later, half a day later or a day later, and then all of a sudden you have new ideas. Okay, so it takes patience, it takes hard work, but this is what we want to move towards. So just as a real quick example, and not a great one, I'll concede, but this was the kite string. So I just kind of clipped out two different ways of getting the kite string. Okay, and I thought just maybe briefly for a minute at your table, you could kind of compare these two to what I'm talking about here with good mathematical solutions versus shape thinking. It's not a perfect example, okay? It's not perfect, but just maybe try to apply those ideas to this. Let me take a minute and discuss at your table.
You would certainly show this because it's probably but in essence it doesn't apply for it's like
Well, it should be -3. Quite understand negative. I understand 3 as well. Does that make sense to me? That's fine.
Okay, any thoughts on this? Can you
I don't understand how it's
kind of
bound.
take this, any of these, maybe some of them, and like I said, not everything is perfect, but kind of talk about some of these ideas for these particular examples.
Well, the second one is clear how it relates to the original question that was given.
So how is it?
Because it tells us where the string ends and it tells us where the string begins.
Okay, so you can see the point, the beginning and ending point right there.
Point, and you
Okay.
can actually understand that that's basically the distance between, or the area between.
Okay, the set of points between them.
Yeah. The second one, I have no idea.
I don't.
Are you talking about the first one now?
The first one, I have
Okay.
no idea.
Other comments on this? What you noticed for these examples in relation to this?
The only thing I thought about for the first one was just by looking at, immediately when you look at the kite string, you think of a line, so then you immediately think of, slope and set forms. So then you just start looking at the image and trying to plot and figure out, okay, what's the slope here? So by counting and using some sort of like slope connection to produce an image. So I feel like the red box would be, the red one would be more like shape thinking.
Okay, yeah, and it's not, obviously there was some thought behind this. I'm not saying that there was no good mathematical thinking behind this, okay? So, but it does seem to,
You have to recreate it.
yeah, so exactly. So if you were to start with 2 new points, you'd have to start all over again. Do you see that? That one you'd have to start all over again. And it's very difficult to look at that and kind of understand from an outsider's point of view, understand what the thinking of the person was here. Okay? Yeah.
Okay, then perhaps we could help explain in words that we'll understand the second one and how that
Is that just code? Then probably.
Well, that was our discussion a week ago. So a week ago we talked about this form of
Right.
1 minus t times an element of the domain plus t times another element of the domain. So yeah, so
Minus
we
element
did
domain. Okay.
we did talk about that and how we had a discussion about how that works. We tried to flesh that out a little bit. So other comments? Yeah.
And it's gonna be much easier to generalize the second one because you can just, if you want to make a line between 2 points, you can just have the 1 minus t and
Right.
t and then just plug in whatever points you want.
Exactly. So again, generalizing, just check it out. So the grade on this particular was just for the image, just for the kite image, because I thought to myself, or I looked at a few of the other one, which was the parametric. Let me find that here. Okay, so what was it? It was from, the first one was from -3 to 1. Is that right? And then from 1 to 4? Does that sound familiar?
Yeah, that looks like what I got.
Okay, so we're gonna reassign this one because the goal was, the part B of this was that it was you did that one function g of x, which was that complicated polynomial. Then at the end of part B, it said, now generalize this for any function from h to k. And then in part C, for this, you were supposed to use that generalization in part B. But I think most people just did this from scratch instead of using the generalization. So this is going to be the new version of this, where you can put in a function f and a function g, and then I can simply, with the slider, I can just change the endpoints. So I want to start at -5, I'll start at -5. I want to start at -1, start at -1. I want the n to be at 4, my n can be at 4. I want this function to be e to the x, it's e to the x. Okay? So totally generalizable, but notice that t is from 0 to 1. And I could do more. I could do h and j and have more functions. And every single one is graphing from 0 to 1, even though I'm changing the ends.
So are the sliders and graphing calculator are what help you to generalize functions?
Sliders are just a way to define a parameter that you can control without having to type it every time. So that's all it is. So I could have just had LF equals -3, and RF equals 1, and LG equals 1, and RG equals 4, and that would have done it. But this is just allows you to then move them without changing those values. Does that make sense?
Okay, what was the -5
What's that? Okay, so when you set up your own slider, so sliders work, your own sliders work just like n sliders. Okay, so it's just like an n slider. So it's saying, so if we want a slider called slider example, that's too long, I guess. Just slider. Okay, so I'm gonna call it slider. You're gonna put in the lowest value that you want for this possible values. So -100. Oh, sorry. This is confusing because we had to put in slider. Slider equals slider. Yeah, so that was a little confusing. But so you can name any parameter that you want, set it equal to slider, and then in the parentheses you're going to put the lowest value, the highest value, and the number of steps.
Is that a control 9?
It's not a control 9, just parentheses. So I can go -100 to 500, and I want, 30 steps.
Okay, the lowest to the highest and the number of steps.
Yep.
Okay.
And so now I'm going, that took me by 20s. And so I'm jumping by 20s from -100 to 500. So it's nothing different than the parameters that we've had before, except that you can define how you want to set the value of it, and then you just slide on the button, and it gives you the value. So it's just like a parameter, and it's just like the n slider we had before that will appear down here if you use n. So I could call just a slider. So I go a equals slider, and then I want that from 1 to 100, and I want 100. So that means I'm going to get every single. I want 0 to 100, sorry. Then I'll get the integers from 0 to 100. And now anytime I invoke a in another command line, it will use the current value of the slider a in that command line. So basically you're doing that same thing again. All right, so you're doing the same thing you did before. You're doing the same thing that you did before, but now it's completely generalizable. It's not for this particular function and these particular endpoints you're going to get an expression of t's. You need to be able to do it for any function, any endpoints, keeping t from 0 to 1. Okay, any questions on that? So it's really not bad if you just apply the things we've learned so far. It's really, and each one is a line. Okay, so each one of these is one command line. Okay, each function is a command line to graph f from there to there, and command line to graph g from there to there. Okay. You can do it. Any questions? So we'll make this one for Monday. We may add some more to Monday stuff. You've got the two readings. The second one, which is longer. Okay, the first one's pretty quick. Second is longer. So if you haven't started, start quick. Start soon. That's why I gave you a week to work on those. But they're important articles. Any questions on this thing about the good mathematical solutions versus shape thinking? Yes, ma'am.
Sorry, where on your website is the reading for next Monday?
There is no reading for next Monday. So the two readings are for Wednesday.
Oh, okay, yeah.
This assignment I'll make due Monday.
Oh,
Yeah.
okay.
So this next graphing calculator assignment will be Monday, but there'll probably be more because once you kind of, it may take you a while to get oriented to the problem, but then you could just crank it out in 5 minutes once you understand it. Okay. Let's see here. What are we going to do next? Oh, okay. Go here. Okay, so what I want to talk about, start a new one of these, get a clean slate. So I want to show you something here that's kind of neat. So here's this R3, so z is pointing up. So what function am I, let's see here. Let's do red. Okay, so I'm going to, right here, I'm going to call this x naught. Okay, so this is x, this is y. I'm going to call this x naught right here. So what I want to know is what am I representing right there? So given that f of x equals x squared, g of x equals sine of 3 of x, sine of 3x, this is x naught. What am I representing right there with that segment? Jocelyn.
This is a little bit off tangent. I had a lot of trouble trying to tell when you have it in 3D which one's x and which one's y.
Okay.
How do you tell?
by the right-hand rule.
Oh, okay.
So the right-hand rule would say that your thumb points in the direction of Z.
Right.
So it would be how your fingers would curl from X towards Y, so that Z is in the your thumb is in the direction of Z. So if you thought this was X, then to curl them towards the other one, then Z would have to be that way. You see?
Not quite. For your hand, which one's which?
Your fingers are pointing in the direction of X, and if you curled them shut, would curl towards Y.
Mainly the arrow on the left is going to be X.
So-
the
so-
arrow on the right is going to be Y.
So basically, if you point your fingers, there's two things you could do to curl from one to the other. You could have your hand oriented this way, so it could curl towards Y. See that?
Okay.
And that works because now your thumb is in the right direction. The other way you could do this is, if your hand was this way, you could point towards that axis and curl towards this one. But that doesn't work because now
No,
you're
Z's
pointing in
not
the negative Z direction.
Okay, that makes sense.
Does that help?
So this is actually negative X direction right here.
Yes.
X naught is negative X
Exactly.
direction.
This X naught is less than 0. That's right. So, back to my question. What am I representing right by that red line? What am I representing? So maybe let's give this thing a spin.
It just changed orientation.
So I'm spinning around the Z axis now. Okay? And if I could stop it where it was before, well, I'll go home. I'm just kidding, we won't. But it would be cool.
Go.
Oh, missed it.
Yeah,
It didn't register my touch. Too soon. I thought there would be a delay. Okay. All right, so now you can see maybe more of what that curve is doing. So what am I representing by that segment?
The segment of the point.
Oh,
It's the F of
this right here.
X naught.
What's that?
F of X naught.
She wants f of x naught. Agree with her?
We're looking at it three-dimensionally.
So why did you say f of x naught? Why did you decide on
It's
f?
actually it's laying on a two-dimensional plane.
Okay.
So it appears to be three-dimensional, but it's not. It's just going up to the y value of X naught.
Okay. And so
And
why
F
not?
F of X squared. That's the common parabola on the XY plane.
Okay. So agree? Disagree? Let's hear your thoughts. This conversation, right? Share what you're thinking. Agree with Marnie? Disagree? And if so, if you disagree, group discussion, not your tables. So, what do you think?
Well, the Z just isn't a variable. The Z is
Right. It's not like actually.
Yeah. We're not giving any
I also don't think yeah, it is. The Z is constant, 0.
That's what I was thinking too. I was thinking like,
But then it's all two-dimensional.
And that would mean the Z value has some way in entry, but
But
we
it's
would
not-
have
it's not all
parameter for what Z would be. We have a two-dimensional.
There, that's better. There we go. Okay. Agree and why or disagree and why? She wants f of x naught. Are you sticking with that, Marnie?
It's asking for the space.
Yep.
I'm asking for this, what this segment's representing. She's saying f of x naught.
I like that. That's the y value. That length.
And what is f of x naught?
I don't know
What would f of x naught be?
X squared.
They're saying x naught squared.
X naught squared.
Okay, so if you disagree or you're unsure, I want to hear what's going on. Okay.
Well, I would say that f of x naught is the point on the parabola like at X naught, not like that like space there, that segment there between the axis and the curve.
Okay, so is f of x naught, is that a geometric element? Is that an object or is it a value? It's a value. So could I be representing that value with a segment, the length of that segment? Would you be okay with that? So by highlighting that segment, I'm really representing the length of the segment. Is that okay? All right, so good. All right, so that's right. She's recognized we've got our basic parabola, and if this is x, then the output is the y value. Okay, now I'm going to do something here. And I'll spin it again. Okay, so what have I done here? What's going on? So maybe discuss this at your table. What do you see here?
Okay, I don't understand how it can have Z value. There's no Z in these. The way that I was taught, like everything had, like you had 3 different variables, and then we had G calculator,
Yeah.
I don't understand.
But
That's what it means. Why do you go
Yeah.
in Z? Like it's actually has Z value. When it doesn't have Z.
There's only two.
yeah. Okay. Okay. Then that's okay. Well, how about something like
So I don't understand.
Okay, anyone make sense of what's going on here? Joel says yes. Tell me, Joel.
It's a parametric curve where x and y are determined by y equals x squared, pretty much, and then z is determined by that sine equation of sine of 3x.
Okay, so the z is determined. You're saying that the height of this curve is determined by the sine 3x curve. Okay. Any other thoughts?
so that's in the Z value as you do the parameters.
Okay. So yeah. So what I'm showing here is if the output of the parabola, the blue curve, if you put that into G, then I'm graphing the output of G in the z-axis.
But I don't understand how you're doing that. Like if I just put that into graph calculator and do it. There's something.
Yeah, there's more command lines.
That's
That's not the whole code.
Okay, now did you just say you made it? You
So
made
this
F?
this here doesn't. This doesn't. These two lines don't. Well, they do all good, but they don't invoke graphing calculator to graph anything. Okay, so it's in. Yeah, and what's left here is parametric. Okay, so we're working with learning these parametric functions. Yeah.
Did you say that F is inside G? That you just said, or did you say G?
No,
is
so
inside
G is being graphed along this curve according to the y values on this curve. Okay,
Right.
so according to the y
So that'd be
values,
composite of F.
it's the z values are
Okay.
right.
Okay.
According to the y values along the parabola, those are the z values. Okay, so let's take a look here. So if I were to pinpoint right here, let's do some green. Oh no. What happened? Where'd it go? Oh. It's totally... I don't know what happened. What did I do? I know what's happening. All right, I just don't want to do that anymore. Okay, sorry. Just stick with this. Okay, so right here. So I want you to find me we'll call this x1. Find me x1. Go. We can work together. What is x1? I want the value of x1. The value of x1 that corresponds to this point on our either you could on the parabola where the parabola and the sine intersect. Right there. So what x1 is that? Anybody have ideas? Or Jason, what do you think?
Like for the x, y, z coordinate, for x I have negative pi over 3.
Okay.
And then to plug that into the f of x, you would get the pi squared over 9.
But tell me about your thought process to get, so don't work backwards. Tell me about how you, what did you do to come up with an answer for x1?
Well, because it's in the negative x coordinates.
Okay.
So then we knew that the x value was going to be negative.
Okay.
And then also looking at the sine graph.
Okay.
Because that's at the z equals 0. It's at that the xy plane. We knew that we had to have something for sine of 0 because the z value is 0. And then
Follow that? Okay.
so
So what would that imply about 3x?
well then 3x had to equal.
Maybe x isn't the best thing. By the way, what is x in this case? What is x in this case? What is it that we're putting into the g function? Okay, which is? What coordinate? Okay, but what coordinate is it? Isn't it the y coordinate? Isn't it the y coordinate? Is that what we're saying? What's going into g is the y coordinate. Okay, so what does 3y have to be? What's that? No, 3y. The argument of sine that will give us 0. Okay, but 3y is pi. 3y is pi, right? So y is? And therefore x is? Almost had it, Jason. So close. What is it? Square root of pi over 3. Is that right?
Oh, wait a minute.
So this negative x here.
What's that?
Send the negative x.
It's negative though, right? It's the negative. So we're saying that this is half of a cycle of sine, right? We want to get it to 0. But that's the arguments. The argument has to get to pi. So what y value is going to get our arguments? 3y to pi. Pi over 3, right? So that says that right here, what's that value right there? It's pi over 3, right? And so what x value will give us an output of this function of pi over 3? Negative square root of pi over 3. Are you with me or not? Everyone following what I'm talking about?
So retrace, you're talking this is, the G is a function of F. So I was thinking of the other direction. What would it look like if it were?
G, so right now I'm mapping G on the y values of the parabola. So on the y values of the parabola is the input into G. And Z is the output. Okay, does it make sense? Any questions? Okay, so then what about any point?
That was in the. Three.
Okay? Let's try that again. Let's do a different one. How about this here? Oh. It's the writing pen. Stop. I was doing so good. Okay. Any point. Okay. What's represented by that segment right there? That's the z coordinate, and how in our, according to the functions we define, what is that right there? What is represented by that segment right there? What value?
X.
So we'll call this x2.
Do you just want general definition?
I want you to use the functions to represent what is that length. Use the functions to represent that length. What would it be? James, got an idea?
We're trying to represent x2.
No, this length here that I pointed at. This length right here.
Vertical height?
Yeah, vertical height.
So that would be given by the sine of 3y.
Okay.
Or it's also equivalent to saying sine of 3x squared.
And so using just function notation, what would it be?
So f of z equals the sine of 3x squared.
Is this a g value or an f value? G. G of what?
Or x.
I'm going any point now.
Yeah.
What's the input into G?
x2.
What coordinate is the input into G? Y, right? Y. Y values go into G. So this G of y2. So then what is this?
F of x2.
F of x2. But what is f of x2? y2. So this is, so G of y2 we can also write as, what can we write that as? G of
F of x2.
f of x2. Okay, so this has something to do with compositions, obviously, right? And so let's kind of quickly check that out. What does this have to do with compositions? So if I were to show you the xy plane, what would we see? So this is the xy plane. Talk to me in terms of functions.
X squared.
We're going to see the function that brings together x and y, which is which one?
X squared.
That's f, right? Okay. What if I showed you the YZ plane? Even if it's sideways, is it okay? YZ plane. In terms of functions, what am I showing you there? I'm showing you z equals g of y, right? Now, if I do this, let's make this one look good. If I show you the xz plane, what am I showing you? So what function are you seeing now? Xz plane. What is it? Z equals G of f of x. But do we see f in this rendering of it? No. What we see is the implicit composition, where we take the middle step out. With compositions, you can think of them as the two-step process, which this notation represents, or you can think of them as just the one step that does the two, right? So by looking at this view of it, all you're seeing is x and z. So it's like a new function like h of x. But all I have to do now is tip the axis a little bit, and you can see the y step. So now this is the explicit way of looking at composition, where you have an x, and then an intermediate step, y, and then the final step, z. So this view of it is representing the g of f of x. Eliminate the y view, and now you just see this one-step process, which is the composition of the two. See that? You plug in x, it spits out z right away, which I called h of x. So it's like these table problems that they do, x, f of x, g of f of x, right? And they do the numbers, and they find f of x, and they find g of x, and they say, okay, now graph this. Graph x and the composition. just take those ordered pairs, right? So this is a visualization of that, where you take out the middleman. Take out the middleman, input, output. But just turn it a little bit and you can talk about what is the middleman, right? That intermediate function step that gets you from X to Z. Pretty cool? All right, so you got your work cut out for the critical crises. Make sure that you stick to the article. The conclusions and are important, right? But make sure it's a summary of what the article said. Okay? Yeah.
Is there any particular length that we should have to either of the
400 to 500 words.
each?
Yeah, each.
Okay.
For any one of these. That's right. Yeah. If you need it for the longer article, you may want to go a little longer. That's fine. Yeah.
Right, okay, that's fine. This one.
Any questions? Other questions? And then I'll post that one that's due Monday that I talked about, the next GC, and you can get started working on that too. Okay? See you Wednesday.
Yeah.